Hi, welcome to the world of calculus. Imagine this. You are watching a car speedometer. You can see how fast it is going at every moment. That is a derivative. But then someone asks, where did that car come from? What was its original position? How do you figure it out? That is exactly what antidifferentiation does. It helps you go backwards from the derivative to find the original function. Today, we will explore antidifferentiation, indefinite integrals, definite integrals, and substitution step by step. Antidifferentiation is like hitting rewind on differentiation. Derivatives tells you how fast something changes, meanwhile antidifferentiation tells you the original function. The result is called the antiderivative. We write it using the integral symbol, integral dx. This is called an indefinite integral because there are no limits. It gives a whole family of functions. For example, integral 4 dx equals 4x plus c. C is the constant of integration. Why? Because if you differentiate 4x plus 7 or 4x plus 42, their derivative is still 4. So we add c to show that there are infinitely many original functions and also x. Later, we will see definite integrals, which gives actual numbers instead of functions. To solve integrals, we have some rules. The simplest is the power rule. Add 1 to the exponent, then divide by the new exponent. For now, we're going to only talk about the power rule. Say we have integral 10 dx. Look at the expression. It is just a constant. The rule is constant times x. So integral 10 dx equals 10x plus c. Nice and easy, right? Now, what if it was integral 10x dx instead of just 10? Then we use the power rule. Add 1 to the exponent, x to the power of 1 becomes x squared. And then divide by the new exponent. So integral 10x dx equals 10x squared divided by 2 plus c, which simplifies to 5x squared plus c. Okay, now what if things get trickier, like a function inside another function? The power rule will not cut it. We need substitution, a way to make complicated integrals simpler. Take integral 2x times x squared plus 1 raised to the power of 3 dx. Looks messy, right? First, spot the inner function, which is x squared plus 1. Let us call this u. U equals x squared plus 1. Now find du. The derivative of x squared plus 1 is 2x. So du equals 2x dx. Think of du as dx's best friend. It tracks how u changes with x and let us swap parts of the integral to make it simpler. So the integral becomes integral u cubed du. Now, just use the power rule. Integral u cubed du equals u to the power of 4 divided by 4 plus c. Finally, substitute back x squared plus 1 for u. Integral 2x times x squared plus 1 cubed dx equals x squared plus 1 to the power of 4 divided by 4 plus c. Substitution just made a complex problem look easy. So far, we've been solving indefinite integrals. Now, let's talk about definite integrals. Definite integrals are different because they give exact numerical values. They also have lower and upper limits. This limits tells us where to evaluate the function. Another important difference is that definite integrals do not include plus c. This is because the constant cancels out when we evaluate the limits. In simple terms, indefinite integrals give functions, while definite integrals give numbers. Find the integral from 1 to 3 of x squared dx. First, find the antiderivative of x squared. Using the power rule, the answer is x cubed divided by 3. Now apply the limits. First, substitute the upper limit, which is 3. That gives us 3 cubed divided by 3 equals 9. Next, substitute the lower limit, which is 1. That gives us 1 cubed divided by 3 equals 1/3. Now, subtract. 9 minus 1/3 equals 26/3. That is the final answer, and that is a definite integral. To summarize, antidifferentiation helps us find original functions. Indefinite integrals give general functions like plus c. Definite integrals give exact numbers and use limits. With practice, solving integrals becomes much easier. Thank you for watching and keep practicing.